My name is Chris Abadie, and I'm going to be doing the solution to problem 4.2.1. So the problem is that we have to find the electric field at all points in space for a spherical shell, inner radius A, outer radius B, with the given polarization. Now, to make things simpler, I'm going to write all of my solutions up here once I get them. This section will be for the first method I'm going to use. This section will be for the second method. So the first method, we're going to find the bound charges and use Gauss's law to find the electric field. The second method, we're going to use the electric displacement to find the electric field, which these answers should be the same. So first, we have method 1. We're going to find the bound charges. So we can find the volume bound charges by the negative of the divergence of P. So we're in spherical coordinates. So that is given by this equation. When we evaluate this, we're going to get minus k over r squared. So I'm going to write this over here so we do not forget about it. That way we can erase the rest. Now the superficial charge density is going to be given by the dot product between the unit normal vector and the polarization. So for the inner surface, the normal vector is in, so it's going to be negative. For the outer surface, it's going to be positive because it's outward. So for the inner surface, we're going to have a negative k over r, where r is a. For the outer surface, we're going to have a positive k over r, where r is b. I'm going to write these over here so we do not forget about them. So now we can use Gauss's law to find the electric field. Now, due to spherical symmetry, we can pull the E out of the integral, and now the integral dA is just the surface area of the sphere. Charge enclosed over epsilon naught. Now, the charge enclosed inside for r less than a is simply 0 because there is no charge enclosed. So the electric field is going to be 0. For r greater than b, again, the total charge, the net charge of this shell is 0 because there are no free charges in the problem. The shell does not have a net charge. So that also implies that the electric field outside is 0. Inside the shell, it's a little tricky. So we have to add up the charge resulting from the inner surface and an arbitrary volume charge for r between a and b. So if we continue on with the equation, it's going to be 1 over epsilon naught. The charge is enclosed. We're going to have the surface charge times the surface area, the surface density times the surface area. Now we're going to have a volume integral for the volume charge. Now, when we evaluate this, the d phi, d theta is going to give us 4 pi. This r squared, it's going to be canceled out because there's an r squared in the denominator of rho b. So this is just going to be the integral of minus k from a to r times 4 pi. Now, that's going to, the a part is going to cancel out with this. This will be 4 pi times a times k. So that will cancel out, and then whenever we divide by 4 pi r squared, we are going to get the electric field of minus k for r epsilon naught. And this is going to be in the r hat direction. Okay, so that was the first way of doing it. We're going to find that the second way is a lot easier. So we first need to write the relationship between the electric displacement and the electric field. So what is the electric displacement? We can use the equivalent of Gauss's law of the free charge enclosed. Now, again, there is no free charge in the problem, so that implies that d is 0. So since d is 0, we're going to move p over here and divide by epsilon naught to give us E. Now, there is no polarization inside or outside, so that implies that the electric field is 0. And we're going to write that over here. So now we just need to find between A and B. We know the polarization is K over R, so that would simply be K over R epsilon naught in the R hat direction for A less than R less than B. And as we see up here, that solution agrees entirely with our solution below for every point in space. So that is the solution to problem 4.2.1.